Now we have like 5,000 planets which have been found outside the solar system. And yeah, what's the point of this? Like, why are we doing this? For me, the most simple question to ask is like, are we unique? Yeah. Is life on Earth unique? Is the solar system unique? Is the Earth and the configuration we find ourselves in special? And actually, remarkably, it does seem like the solar system is not the run-of-the-mill system.
What's up, you scholars of enlightenment? Welcome back to the channel. Today we have another Bad Boy Meets and a particularly amazing special guest speaker. We have Professor, that's Professor, not Doctor, because he's waiting in the wings to one-up me. Professor Dr. David Kipping.
Just use all of those.
Just use all of them in a big row, exactly.
I'm the professor!
Say hi, Dave.
Hey guys, how you doing? I'm looking forward to chatting with Sam today. Me and Sam go way back, so this is going to be fun today.
Yeah, exactly right. So Dave is an assistant professor of astronomy at Columbia University in New York, because he's that cool, where he studies extrasolar planets and moons, and he also leads the Cool Worlds Lab at Columbia, which I very strongly recommend you go and search for on Google. There's some really cool videos about extrasolar planets, extrasolar moons. Really useful resource. He's best known for his work on extrasolar planets, extrasolar moons, and also interested in characterization of transiting exoplanets, their detection and categorization, exoplanet atmospheres, Bayesian inference, and he's the principal investigator, PI, like Magnum, on the hunt, on the hunt for exoplanets with Kepler Hex. I think that's your baby, isn't it?
Yeah, what the heck?
Yeah, exactly. What the heck is your baby? And he's also, which I found utterly terrifying, done an awful lot of teaching of students. Is that right?
Oh, come on, that's not so terrifying. It's scary the first time, but
no, I mean terrifying that they allow you to teach.
Oh yeah, well, I think the students are more terrified than I am, to be honest, in that classroom. But you just go in strong.
Just like back in the Cambridge days.
It's kind of like everything. It's just that you just go in there and you just have to learn on the job. And the first time you're crapping yourself, and the more you do it, the more like, okay, I think I kind of get this. But on the first, I have some hilarious stories. The first few times I taught.
Let's have one.
Right. So I taught astrobiology the first time I arrived here, and I picked up the class halfway through. So another professor was teaching it. She had a baby, and then I took over halfway through. That's actually kind of a weird way to take over a class, because they've got to know this professor, and then suddenly you just appear and like, I'm taking over now, guys. And I decided, naively, I thought Americans don't know anything about evolution. That was my stereotype fallacy going in. So I thought, I'm going to teach him some evolution here. And I went to the Department of Anthropology, and I asked them for some schools of human hominid schools. And they were like, why do you need these? Like, you're in astronomy, aren't you? I was like, yeah, we need these. Like, I need them for my class. And she was like, all right. I mean, these are really expensive.
Don't ask too many questions. It's all right. I'll bring them back.
It'll be fine. And she was like, each one's worth like $10,000. So you need to be really fucking careful with these. So it'll be fine. So I took this box of schools down the street. Brought them to my class. I was so excited, so pumped. I was like, "This is gonna be the best class ever." Laid them out on the front of my lecture hall. Students come in, they're like, "Oh, this is gonna be good. We're getting into. He's got some props here," and I didn't know anything about hominid schools at all, and I didn't realize that until I started the class.
Oh dear, I'm in trouble.
Yeah, I just stood there and I was like, "Okay, so I've got some schools." They get smaller as you go down and bigger as we get older, and it's evolution.
Yes, science, bitch.
And that's kind of all I had, and it was just. I had to really it's an hour 15 lecture as well. They're always hour 15. So
to really string it out.
I had to wing that one. Yeah. So that was fun. I learned a lot. I learned not to do that. Prepare a bit more for your class before rocking up like that.
Learn by doing. Learn what not to do.
Yeah, exactly.
If you'd have told me 15 years ago when we were messing around at the back of those lectures in the pit bar and winding up, Liddell and the like, that I'd be a doctor from the LHC and you'd be an associate professor at Columbia, I think I'd have said, "What are you talking about?
Are you mental?"
We were not the likely picks.
We were not the likely picks to do super well in physics, but we made it work. And you've done some awesome stuff. Now you kind of work with NASA. You've done a correction to Einstein, which is amazing, and we're going to talk about later. And you're away teaching the kids. And the biggest thing that, of course, you specialise in is these extrasolar planets and these extrasolar moons. So I think that's the first thing we'll probably go on to discuss. So tell us about the Cool Worlds Lab mission, the thing that you are now the head of.
Yeah, sure. So when I got hired here, that was kind of my pitch to Columbia, is that I was going to start this group called the Cool Worlds Lab. And
is it Columbia where the Ghostbusters were, by the way?
It was, yeah. We're kind of famous for that. Like on the steps they filmed there, and yeah, there's quite a few films, and Law and Order I think is filmed here quite often. So this is a fairly popular area for filming.
Just to cut you off in full flow with like a random.
No. And
your theories are the worst kind of popular tripe. Your methods are sloppy, and your conclusions are highly questionable. You are a poor scientist.
Unfortunately, the Cool Worlds Lab isn't quite at that level yet, but it's just a matter of time. We're heading straight there. We'll be in Ghostbusters 4, 5, whatever. Exactly. I'm sure we'll be there. So we when I arrived here, my focus was these cool worlds. When I say that, people always think I'm saying like dope. Like,
damn, it feels good to be a gangster.
Yeah,
hip.
That's what I thought it was. That's what I thought.
Yeah. That's not what I mean. That's actually we're really interested in planets which are far away from their star. So they're cold because they're far away. There's a big focus right now on cool stars, by which we mean, again, the same thing. They're just like these diminutive stars that, like M dwarfs, and we think those are the most common type of stars in the universe, and maybe there's many, many more Earth-like planets around those than there are around Sun-like stars. And so my name, I guess, is a twist on that.
Yeah.
That we're interested in the cool worlds. And I say worlds because, as you alluded to, I like both planets and moons. So I wanted to find a name that could capture that.
I see. So you were already setting up the groundwork, so you didn't want to box yourself into the...
So we're trying to push into this new regime, planets which are colder than most, and we're trying to hit both moons and planets together.
I like it. You didn't box yourself in. So why should we care? Let's start with the planets before we go on to the moons, because it seems like it's another level of difficulty going down the size spectrum there. Why would we want, apart from it being fucking cool, to find extrasolar planets? What's the big deal here? Why are we committing a lot of funds and a lot of smart people like yourself to doing this?
Yeah, it's that's a good question. It's been a quest for 25 years now that since the first exoplanet discovery. I think it was in the first universally accepted one was like 1991, and the first one around a normal star like the Sun was 1995. And since then, it's been getting ever more planet discoveries each year. Now we have like 5,000 planets which have been found outside the solar system. And what's the point of this? Like, why are we doing this? For me, the most simple question to ask is like, are we unique? Yeah. Is life on Earth unique? Is the solar system unique? Is the Earth and the configuration we find ourselves in special? And actually, remarkably, it does seem like the solar system is not the run-of-the-mill system. You look out there and like 90% of the solar systems we see don't look anything like our own solar system.
Which I guess is quite bad when we sort of project our understandings of what a system is like onto that. Maybe when we're looking for these things or whatever, is that a problem when we go looking? Do we have a bias to things that look like ourselves?
Absolutely. For example, we mostly, especially the early days, we mostly focused on stars that were similar to the Sun.
Yeah.
But those only represent about 10% of stars in the universe. So we clearly, coming out the gate, we were incredibly biased. And of course, we're still obsessed with finding Earth-sized planets.
Yes.
And because we assume that's where life will be because that's where we live, we don't really know that's true. I mean, as one of the reasons I'm interested in moons is that's another place you might be interested in looking for life. And people have really pushed the envelope recently, thinking about other ways that maybe even life on asteroids, life in gas giant atmospheres, Trojan objects, maybe even for brown dwarfs, you could have life on the surface of these failed stars. So people are really pushing the envelope, and hopefully we can get out of this mindset that, hey, we're it, guys. Like this is the pinnacle, and therefore everything else in the universe must look exactly like us.
They're coming for you, Dave. They're coming for you by the sound of it.
I know, can you hear it? This is why making my YouTube videos is so hard.
Yeah.
I'm on the 13th floor up here, but this shit goes on all day.
Well, I hope there's not a fire beneath you if you're that high up.
Yeah, I'm dead. If there's a fire, that's it. The good thing about being this high, this building was in the Manhattan Project. Some of the early experiments were done here.
Oh, wow.
And in the basement, they've just poured concrete in it to like cover the radioactivity. So I'm kind of glad I'm up on the 13th floor. I don't want to be right
get that inverse squared law working for you.
Yeah, exactly. You need that.
So good. So we use it to discover whether we're unique. I guess to also think about how our solar system might have formed. How do we actually go about finding them? Is it all transits, or are there other methods for finding these things? And could you tell us what a transit is?
Yeah, let's see. I guess there's probably maybe 5 methods which are most popular right now, but it's kind of an endless list. You can always come up with sort of random ways that will never work. But the most popular method is the transit method. That's really simple. That's just when a planet passes in front of a star, blocks out some of the starlight, and you can't see the planet directly. I mean, it's too far away. It's too close to its star, and the star's way brighter. But you can do pretty good photometry, as we call it, of the star. Photometry just means you basically take a photo every minute or whatever, and you just measure the brightness of that thing in each exposure. And so if the brightness goes down, you're like, hey, there's something blocking it in front. Maybe it's a planet.
So this is sort of like that scene in, Sunshine, where they're watching Mercury go across in front of the sun. And
I think I've used that clip, actually.
Have you?
In one of my
I think you might have done when I was doing my
videos.
research earlier. I was like, damn. He's already used it. I'm going to have to find another.
Oh, I love using my sci-fi films in those videos. Yeah,
that's a good film. It goes off the rails, but I like that film.
It's pretty dark, and I like the music to it as well.
The Kappa's Jump is like the best song ever.
Yeah.
Anyway.
Yeah.
Moving on. Right. So transits, a planet goes in front of the star, a distant star, blocks out some of the light, and we can see that reduction in light means something has passed in front of the star. We can infer that it's a planet. What are the other methods that we use? I'm trying to think back to our old lectures with Chris Haniff that I remember things about stellar wobbles
we had like 2 lectures on it. It was nothing.
And I think both of us were like looking at each other halfway through and like, I just don't get any of this.
The fuck is he talking about?
Yeah, now let's go back to general relativity. Yeah, that's the more important thing to
that'll
look.
help, yeah.
Yeah. So the stellar wobble comes in 2 flavors. One is to look for the velocity of the star. You can measure velocities of stars pretty well by Doppler shift. That's the same thing like an ambulance driving down the street. You hear the pitch increase when it comes towards you and decrease when it's going away. So we can do the same thing for light and thus detect if there's a wobbling star. You can also just physically see if the star's wobbling by looking at its position. And that's actually the first method people thought of for looking for planets. And it was a complete failure. They basically tried for 150 years with literally in 1855 was the first claim of an exoplanet. Like, it's ridiculous. 1855, Captain William S. Jacob. I say, I've got doctor and professor. I don't have captain.
Captain.
Like, that's serious.
The skipper.
Yeah. So he wrote this incredible paper claiming by eye, he detected an exoplanet by looking at the wobbles of the star.
Wow.
Of course, it was bogus.
Yeah.
But I just admire the dude for the bravery of trying to pull that off.
That's balls out, is that? Just going straight for it. I can see that.
So that method still basically hasn't worked. I mean, we're still planning on it on new Gaia, which is sort of where it's now flying and it's bringing data. It still hasn't, I don't think, detected any exoplanets with this method, but it should find a heap load when we get the next big data dump down from Gaia, but it's yet to be sort of proven. And then another cool method is microlensing. That's when coming into sort of the Einstein regime, that's when you have a star, or hopefully a star with a planet, pass in front of some distant light source. Okay. So that is often just the center of the galaxy. It's just very bright in the center of the galaxy, lots of light there. And if something passes in front of it, it's going to actually lens the light from the background. So you see that background light get brighter for a short amount of time.
So the light gets bent by the gravitational field of that thing passing.
Yeah, it's like a magnifying glass just passing over the center of the galaxy, and you just see, you don't even necessarily see any light coming off the magnifying glass, but you can tell the magnifying glass is there because that background thing suddenly got a lot brighter. And that's really how the microlensing method works. And that's been fairly successful. That's found something like 20, 30 planets, I think.
Nice. So the main and simplest version of doing this is usually with the transits. Is this what telescopes like Kepler, I think there's TESS coming online soon, is it? Is that the method that these telescopes use? Is this the most successful method for?
It's the most successful in terms of just pure numbers.
Yeah.
And that's just because it's so simple. I mean, you really just stare at the sky at 200,000 stars and just take these photos over and over again. So it's very, very simple, but it does have limitations. It prefers finding planets really close to the star, which is not ideal for me in the Cool Worlds lab. We want planets far away from the star. Microlensing's great for planets far away from the star.
Okay.
It loves those sorts of things. So each method has its own sort of pros and cons. And I wouldn't say any method's like way better than the others, but I definitely have a soft spot for transits. That's been my bread and butter for my whole career. So yeah.
Nice. So you say there was about 5,000 planets now. Did you say
I think around then, yeah.
And what physical characteristics of these planets can we find? So rather than just saying, yes, there's a planet there, or no, there's not, what physical characteristics can we get at?
Not very much.
Not very much.
You see these artists' impressions, and it looks like, whoa, like this planet has
little
clouds,
people waving on them and stuff.
It's the artists' impressions really kind of we're a victim of our own success of those damn things, because people think we know way more than we do. We really just know pretty much two things, I would say. One is how big the planet is, and that's just from how much light it blocked out. So you get a radius for the planet, not a mass, just how large it is, but not how heavy it is. Which means you don't know if it's made out of styrofoam or made out of rock. It could be anything in between. And then the second thing we get is the orbital period. So that's just by timing how long it takes between these transits. You get these events, and you can just sort of figure out what the period is between those. So that tells you the year. You can then, if you remember your Kepler's third law, you can go through and get your 7 major axis, and therefore you can figure out the temperature with a bit of black body equilibrium physics. So you can work out some stuff, but it starts to become increasingly derivative and increasingly assumption based. Like when you do a black body temperature calculation, like if you do that for Venus, you get completely the wrong temperature. So it's not necessarily that trustworthy when people talk about planetary temperatures.
So how do we go about so if we can get the radius, how do we go about getting that mass so that we can say, this is a rocky planet that's just like Earth, or this is a gassy planet that's one of these hot Jupiters that's close to their stars? How do we get at that mass if we can't get that from the transit?
Well, you can go and try and do your astrometry, or try and do your radial velocity measurements and try and get a mass that way. Radial velocity is the most common way. That's, typically if you think you've got something really exciting, you would go to Chile or Hawaii, and you would grab some time on that telescope if you're lucky. It's very competitive. And you would try to measure the spectra of these stars over a few nights and see if it's wobbling and get a mass that way. I generally
doing sort of the mv squared over r and assuming a circular radius kind of thing. Is that how
actually you can measure? You don't have to assume it's circular. You can actually figure out if it's on an elliptical orbit from the shape of the way the star's wobbling. So if it's wobbling in a circular orbit, it's just a sine wave. But if it's wobbling on a eccentric orbit, if you imagine it's almost like a comet, it kind of swings in really fast and then slows down, and then swings in really fast and comes down. And you see that the sine wave like pulses, and it's really flat and then pulses. So you can actually measure eccentricity from the shape of those things. That's great. The other way you might use, which is a little bit trickier, but I prefer, is something called transit timing variations. And that's if you have multiple planets in the same system and they're near to what we call a resonance with each other. So they almost share sort of an integer ratio between their periods. Then they can gravitationally interact very strongly and that causes the planets to wobble. So that means that every time you see a transit, sometimes it happens a bit early, sometimes it happens a bit late, and you can use those deviations to actually back out a mass between the planets. Wow. So I really like that technique because I don't need to go to Chile and Hawaii. Because
why do you not want to go to Hawaii?
Well, I have been to Hawaii. It is beautiful, but I'm a terrible observer.
Yeah,
I'm not the person you want on that telescope. Give me the data science, give me the statistics, or just coming up with crazy, wacky ideas here at my desk. Good.
We're going to come on to
ask me to go to the telescope, and I'm going to break your $10 million telescope. So
I can believe.
So yeah.
So once we've sort of seen the size of these planets, the mass, their likely makeup, what do we find with these extrasolar planets? Are they mainly rocky? Are they mainly gassy? You said they don't look a lot like our solar system. So what type of planets have we found, and how are they different to what maybe we expected to find?
We found a big diversity of things. The smallest things we can currently detect are about the size of the Earth. So we don't know what's below that limit. Maybe there's more surprises below then. I'd say probably the two biggest surprises that we found over the last 10, 20 years of exoplanets has been, one, the existence of these hot Jupiters. I mean, when you're taught, as we were probably taught, I can't even remember how planets form. You're normally taught that all the gas giants have to form really far from the star, beyond what's called the snow line, and that's where ices can condense and then they can stick together and build these big planets. But here you've got these icy giants, these gas giants, parked almost on the surface of the stars. It's like, who ordered that? Like, how did that get there?
Hey, who ordered the poo-poo platter?
And they're so weird that when they were discovered, like, people thought it was BS. They were like, I don't believe you. There's no way you can make a planet like that. It took a long time for people to come around to it. So that's still, we don't have a good explanation as to how you make a hot Jupiter. There's some ideas, but none of them are particularly convincing over the others, I don't think. And then the other big surprise is that mini Neptunes, which is a planet we do not have in the solar system. This is a planet which is in between the size of Neptune and the Earth. So that Neptune, just for context, is 4 times the radius of the Earth. And these planets are about 2 Earth radii. And that is the most common type of planet in the universe.
Interesting.
And we have no fucking idea what it is. Like, is it a ball of gas? Is it a ball of ice? Is it an ocean world? Is it a rocky world? We have no idea what these things are really made of. There's no point of extrapolation. I mean, you can extrapolate up from the Earth, or you can extrapolate down from Neptune, but they don't really meet in the middle. So you're kind of, we really are very confused about the nature of those things and how they're formed. And just the commonality of them, the fact that is the most common type of planet in the universe, yet we do not have one, is weird.
Good, very good segue, because I was looking at one of the great videos on the Cool World site, and there was a young man there, investigator, who was saying maybe there's a planet out there beyond Pluto in the Kuiper Belt. This planet 9, or I think they called it, that is potentially one of these Neptune-ish type planets that we haven't detected yet, just because they're so common. Is that
would be exciting?
Yeah.
We don't know if it's there yet. They've been looking for a few years now, and they don't see it. But there's an awful lot of sky to survey to completely rule it out. And of course, this thing is so far away. It's like 500 times further away from the sun than we are, that it reflects basically no light back towards us. It's very difficult to detect. But yeah, if it was there, it may very well be the first super Earth or mini Neptune, and then we should be sending a probe to that thing if we found it. So that would be one way to maybe resolve that.
It's a nice point of crossover between our fields, actually, because I think the last video I saw had CERN opening some sort of hell portal to this planet. So maybe we can help you out when you finally find it, and we can send
like
you there to have a look.
Like a wormhole or something.
Yeah, exactly. They're always on about this. I was watching in some of your videos that the nutters who were always like, you've torn up Einstein's theories. We always get the same people. Einstein's theories are rubbish. You try to open a hell portal at the LHC, just admit it. Always get this type of. We always get this type of stuff.
Just admit it. Come out with it. Come on.
Yeah, exactly. Just tell it. It's fine. But what I found interesting from the research is these rocky planets don't seem to go much bigger than the Earth, like 2 Earth radii, and then we sort of go into the gassy planets. So is that the Earth is actually might actually be a super Earth? It might be on the bigger side of the rocky planets.
Yeah, that's great, because we actually sort of pushed that idea a bit in our group as well. Yeah. So one of my ex-graduate students who graduated last year, which is kind of wild, right? So I've now helped a student get a PhD.
It's cool. I'm proud of you. I am proud of you. I won't give you too many compliments, but I am proud of you.
Thank you, Sam. Yeah, and we wrote a paper together, and it was really simple. We just plotted the mass on the x-axis and the radius on the y-axis, and just put all the planets and stars that we knew about on the scatter plot. And you see this kind of surprisingly tight relationship, and you get these kinks in that plot. And at those kinks, it's like, well, something's changing.
Some new physics is going on.
Yeah, so you see one, for example, huge kink when stars are born. So once you have enough pressure for nuclear hydrogen fusion to happen, suddenly the mass radius relationship suddenly changes. And similarly, you see something happen at about, I can't remember off the top of my head what it was. I think it was about 1.2 Earth radii, which would be about 2 or 3 Earth masses, so very close to the mass of the Earth. You see another kink. And before we wrote that paper, certainly if you go back 5 years before that paper, the general consensus was that 10 Earth masses would be the transition between rocky planets and gaseous planets. And we're seeing transition much lower than that from the work that we did, and many others are seeing similar stuff. So it looks like the Earth really is one of the biggest worlds. That's actually maybe not that surprising, though, because if you have $1 in an account, or a pound over in the UK in a bank account,
going down all the time, the pound, it probably will be $1. It probably is about the same.
It's much more likely that your pound would be in one of the big banks than one of the small banks, just statistically. If you just took a random pound out of all of the financial system. And in the same way, if you're born as a random soul on the Earth, you're more likely to be born in a highly populated country like China or the US than you are in, I don't know, like Henderson Island in the middle of the Pacific. And so that's kind of the logic. That there's actually been a cool statistical paper by Fergus Simpson on this, and he argues that we are likely to live on essentially the super Earth because it has the most living space on it. It'd be really weird if we lived on this tiny island just from a statistical perspective. We probably are in one of the most highly populated worlds in the universe. You should bring him on your show one time, because he even has something called the big alien hypothesis, where he I can't remember which way around it is now, but he thinks he can determine the physical size of how big aliens will be using a similar statistical argument, really pushing it.
We're going to get him on. I want to see that. I want to hear about that. So how many of these Earth-like planets, so as a percentage of the stars that we look at, how many of these stars have a sort of Earth-like planet around them? What's a rough estimate of that? And what sort of stars do these Earth-like planets tend to congregate around?
Yeah, well, I'm going to frustrate you because I'm going to say I don't know, and that's the most honest answer. We do have some.
I think you said about 2% in one of your videos was the best estimate, but
I mean that's my favorite.
It was like plus or minus 50% or something. Yeah.
2% plus or minus 2%.
Yeah.
So what happened is Kepler was supposed to do that. Kepler was supposed to figure that out for us. It was supposed to detect Earth-sized planets around sun-like stars, but it didn't detect any. There are no examples of an Earth-sized planet around a sun-like star.
Wow.
Kepler ran for 4 years and didn't find any. Probably the reason at least Kepler cite, the Kepler team cite for this, is that turns out the sun is unusually quiet. They based all of their stellar noise models off the sun. And it turns out the sun, compared to the rest of the galaxy, is a much quieter star than most stars. So most stars are noisier, and therefore it's just really this is like granulation and stellar physics happening on the surface. And that just screws up your measurement. And Kepler didn't anticipate that. They just thought the sun was typical before, which is not an unreasonable thing to think.
You have to go with what you know to start with.
After 4 years, they realized they didn't have enough data. They asked to get more data. They were approved for more data, and NASA said, sure, you can run for another few years and finish the job you started. And then unfortunately, its reaction wheels blew, and it couldn't point at the same stars anymore. and it had to switch to this new mode, but unfortunately it can never look at the same stars again. And now even that mode's done. It's completely dead in the water now. So unfortunately it just didn't collect enough data. So whenever we talk about the frequency of Earth-like planets, it's an extrapolation. You have to take, okay, what is the trend in radius at a 1 year period?
Yeah.
And what is the trend in period for a 1 Earth radius planet, and sort of extrapolate those two things to a point. But extrapolations are very dangerous, and it depends what you assume. You get wildly different answers. So this is why we really don't know. But my favorite estimate is more on the conservative side. I think it is probably in the percent levels of sun-like stars.
That's for everyone listening, though. That's a proper good scientist answer. I don't know. I don't know is fine. Like that's a proper
As I said recently in one of my videos, we should not be afraid to admit when we don't know the answer.
It keeps him in a job as well, so it's smart on all fronts.
Still things to do.
Work to do, yeah. So what's the next big telescope? Is it this James Webb one that's?
If it ever flies, we've been waiting. That thing was supposed to fly, I think, 2011 for $800 million or something ridiculous, and it's now cost $8 billion, and we're expecting it I think in 2023. It's like the most insanely over budget and pushed back mission in the history. Even, I mean, Hubble was pushed back a lot and went way over budget, but this is like extreme. It'd be great just to get it out the door at this point, because this thing is eating up so much money whilst it's on the ground that we can't do any of the astrophysics. It's just, we can't build new telescopes because this James Webb is costing so much.
Do you want to bet which one happens first, James Webb or Brexit? Or...
They're both like Zeno's paradox. They're just you never seem to get any closer.
It's like the end of Bruce Forsyth's career, just always 20 years ahead.
or fusion power. That's another example, right? We're always told fusion power is going to be like 20 years away.
Next week, it just never turns up.
Yeah, I need my fusion power, man. So. So I guess I'm optimistic that James Webb will fly more than I'm optimistic I can say about Brexit or anything like that. But the after that, the Europeans are building a big telescope called Plato. Plato will be almost like a super Kepler, so that would be a very exciting mission. And there's another mission called WFIRST, which is going to be doing the microlensing game. Although the president's budget has tried to cancel that several times now. So we keep having to fight for that pretty hard to push it back into the budget.
Nice. So is it also possible to learn anything else about these planets in terms of composition of atmosphere, for example, so that we can get maybe a handle on whether they're likely to have life? Is it possible to get information on that kind of thing? Yeah,
that's the dream. That's where we'd like to get to smell the atmosphere of an exoplanet. It's very difficult to do it, but James Webb might be able to do this. In a nutshell, what you do is you do this transit method. You watch the planet pass in front of the star, and you just do that measurement in different filters. Like you put a different, like a red filter in front of your telescope, then a blue filter, then a green filter. And if there was no atmosphere on that planet whatsoever, it's just a ball of rock, say, then it would be the same transit depth in every wavelength of light. But if you got like an atmosphere like we have, that the sky is blue because of Rayleigh scattering, then the blue filter will see the planet look bigger because that blue light is being scattered on its journey through the atmosphere. Okay. So you can actually figure, and we see that we've actually detected Rayleigh scattering on many exoplanets now. It's actually one of the easiest things to detect. But you can also maybe refine this and detect even individual molecules. Such as ozone. Ozone likes to absorb at a very specific wavelength of light, and if you see the planet suddenly appear bigger at that wavelength of light, then you're like, this planet has ozone. Ozone really shouldn't be in a planetary atmosphere because it's a product of oxygen. Oxygen oxidizes stuff. It's like really reactive. So something kind of has to be making oxygen for it to be hanging around. And that's what we'd call a biosignature. So a potential signature of life in that case.
So by doing spectrometry basically of the atmosphere and looking in different filters, we can potentially get a handle on what the atmosphere of an exoplanet might be like. And then I guess we're going to do the same dangerous game of extrapolating from what we think life needs on the Earth, water, ozone, these kind of things.
I mean, what do you look for? It is hard. I mean, we're looking for oxygen because we breathe oxygen. We certainly want to look for planets which can support water, because all life on Earth requires liquid water to survive. But that's just us. I mean, who knows that methane isn't also, these methane lakes on Titan, for instance, have been often cited as a place that maybe to look for life. So more generally, maybe you just want to look for chemical disequilibrium on planets. You could see, I mean, oxygen is an example of that. Like, there's too much of it. It just shouldn't be there in an equilibrium system. But there's been some chemical work being done looking at the huge, I mean, this is hard because you have to almost like simulate millions, billions of possible chemical reactions on a computer and see what's possible. And even doing those simulations on a computer is really hard. Like, can you actually realistically do the physics of how chemistry happens? But people are looking at all the different types of disequilibria that might arise from exotic forms of life. And the downside of that is that if I detect a disequilibrium, sure, maybe it is life, but it starts to become such a broad definition that, I mean, like on Mars, we have these methane plumes that maybe you've heard of, right? There's been detections of methane quite recently as well, reconfirming this trend. But methane could also be produced
Mars cows,
abiotically, just from sort of the geology. There could be like a reservoir of it that's just, coming out on a seasonal basis, and that looks like it's life that's doing something, but it's not. So it's going to be, and that's just that's our next door neighbor. So doing this from 50 light years away is not going to be easy. So I'm kind of skeptical that biosignatures would ever lead to an unambiguous discovery of life. And that's why of course I still think it's worthwhile to do it. Maybe we could do it on a statistical level. But that's why I also spend some time thinking about what we call technosignatures and SETI, which is looking for what I would call unambiguous signatures of life, because it's intelligent life. Someone like send you a prime number sequence, like that's not a Martian methane reservoir. That's somebody on that planet trying to say hello. That
was one of the interesting things you mentioned in your video, is that one of the ways that they could signal to us would be to artificially influence that transit signature from them passing in front of their star, whether that's with a laser or whether it's putting some, letter shaped or geometric shaped moon in front of them to block some of the light. They could actually encode some information in that transit signature that we could then detect. Yeah,
that was kind of a cute idea. I mean, the challenge of doing SETI is that it's just there's an infinite number of things you could look for, and an infinite, well, not an infinite, but a very large amount of sky to survey. So you kind of want to hone in on like particular frequencies or particular techniques. So in radio SETI, there's this thing called the water hole, and it's basically a radio frequency that is particularly quiet. And it's kind of like the water hole where animals in the Savannah Desert come around and they collectively arrive there. And there's the idea that maybe civilizations realize this. They realize that the universe is radio quiet, and they will choose that frequency for communication. And in the same way, this is almost like a temporal water hole. It's saying that this moment in time, when they know that they are transiting from our perspective, they're smart enough to figure that out. They would know that would be a good time to send a message, because we're probably looking at them at that moment in time because there's something interesting going on. So it wouldn't be a crazy time to send a message, and you could actually send quite a lot of information that way.
It's really, really interesting. And you could, like you said, another cool idea in the videos is you could actually cloak the planet from us, going on the other side of that by filling in that transit, by firing some lasers at us. So, nobody's here to cover up for that.
That's when they troll you.
That's when they absolutely
trolling you from the other side of the universe.
Exactly.
But, they may very well do that.
That's just me and you on the other side of the universe. Dave, it's been an absolute pleasure. I know you have to get off to pick up your kids now. I think we're coming to the end today. Really fascinating stuff. Really, really interesting. Hope we can have you on again to talk about some more stuff. Thank you very much for joining us. If you're still watching up to this point, please go over to Cool Worlds and subscribe to their YouTube channel to see more awesome astronomical stuff like this. And Dave, where can people find you? Where can they keep up to date with what you're doing and the content you're producing?
Yeah, I guess the two things are the Cool Worlds Lab channel. So it's just youtube.com/Cool Worlds Lab, or link down below somewhere, I guess.
I'll put it in.
And
Highly
Twitter.
recommended.
On Twitter, I have a David_Kipping if you want to follow me on there. So those are my two means of following me.
I'll put them in there. Dave, final question. Can I join Cool Worlds Lab?
Dude, you're an honorary member of the Cool Worlds Lab for sure.
Thank you.
We need some particle physicists, clearly, in our group.
I appreciate it. I might be coming to you for a job very, very soon.
Okay.
Dave, thank you so much. Thank you for taking the time to talk to us. Hope we can do it again. And have a good afternoon. Have a good evening.
Thanks for having me, Sam.
My pleasure. Always a pleasure, buddy.
Yeah, see you later.
Bye now.